All right, welcome back to Fluid Mechanics homework number 2. This will be part C. Part C is broken up into only one problem statement, which is asking to derive an expression for the horizontal force on the circular end cap of a cylindrical tank of radius r when it is filled with liquid of density to a height of h. You can leave the final expression in an integral form to be evaluated numerically for specific values of r and h. So this problem is actually kind of similar to part A of this homework, where we had our circular end cap, but the difference being that part A had it filled up to only half, and we're going to fill this up to a height of h with our fluid. So this will be big H. And we'll once again have our radius of big R. And we're going to think about this in a similar manner where we're going to take rectangular strips to find our force. So we're going to have a rectangular strip at some depth h, small h, with a height of dh and a width that is constantly changing due to the circular nature. So, what's our force going to look like? We're going to have F is equal to pressure times some area, which is equal to, we know the pressure at some depth is equal to rho GH. So we're going to have rho GH. And our area in this case will be our width times DH. DH. And so we're going to think about this in two different integrals. So we're going to have one integral for the top half of our circular end cap, and also another integral for the bottom half. And the reason for this is that we need the width, and the width is going to be from finding two different thetas, two different angles that are different from the top half and the bottom half. So we're gonna have F equals so this distance down to the top half is going to be our x1, and this distance down to here will be x2. So we're trying to find our width here. So remember that we will use theta, and we're going to try and find this width, but it needs to be multiplied by 2 to get the entire width. So we'll get force equals 2 rho g integral from h r sine theta dh, and this is our top half integral. So this is for the top half of our circular end cap. And we're going to add it to the bottom half, which looks like the same integral. However, they're going to have they're going to have different limits of integration, which is why we have to separate them now. So this is the bottom half. So I guess now we should figure out what our x1 and x2 actually equal. So x1 in this case is going to be equal to, let's see, h minus h minus big R. And x2 is going to be equal to r minus big H minus h. So how do these x's relate to our theta? So theta will be equal to the arc cosine of so theta will be equal to the arc cosine of each respective x. This is the top half theta, and this is our bottom half theta. So x2 in this case over r. So cosine of theta will be equal to x1 over r. And x2 over r respectively. And now we can replace, we can try and put our x1 over r into our force equation. Because remember, we're having two different variables here, so we need to get our theta out. So sine of theta, we know, is equal to the square root of 1 minus cosine squared of theta. So now we get sine of theta, and sine of theta we can get to simplify here. So we have 1 minus, we know cosine of theta is x1 over r squared, and that will simplify to r squared minus x squared over r. So now we're ready to replace our sine theta into our integrals. So we get f is equal to 2 rho g. We're going to set our limits of integration. So we're going from 0 to r minus h. So from 0 to r minus h of h, big R. We're going to replace our sine theta with the square root of r squared minus x squared over r. Dh, we can see that these two r's cancel, so they're gone. Next, we're going to do our bottom half, so we get 2 rho g from starting where we left off of r minus h all the way to h of h. Once again, we have r, and this is x1, by the way. I forgot to write that down. Square root of r squared minus x2 squared, since we're working on the bottom half, over r dh. These two r's cancel out. Now let's keep writing this out. So we get our f is equal to 2 rho g, r minus h, 0. And now we're going to write out our x1 squared. So we have r squared minus x1 squared, which we know x1 as being big H minus big R. So we get big H minus R squared all over the square root dh plus our 2 rho g. This is our bottom half once again from r minus h to h of h square root of r squared minus x2 squared in this case, which we know as r minus big H minus h squared dh. And we notice that this square and this square, when these terms are both squared, they equal the same thing. So we can actually combine our integrals here. So we'll get f is equal to 2 rho g from 0 to h of h r squared minus h minus h minus r squared dh. And this is the expression for the horizontal force on the circular end cap of a cylindrical tank of radius r when it is filled with a liquid of density to a height h, and leaving the final expression in an integral numerically for specific values r and h.